Okay, let's start here. Ooh, we're missing some students though. Ooh, that's bad. I'm gonna have to send out a dirty email or something to people. Okay, so I keep moving this homework 2.1 due date back, but most people are finished with that or well into that. So it's due tonight at midnight. And I've shifted some of the other dates back to give you all a little bit more time. So I've relented here a little bit and moved the test back to, from next Wednesday to the following Monday. So I don't like to give tests on Monday because I know that people really don't do much on the weekend in terms of their homework. Yes, I know this. Okay, I have proof of this. And so I don't like to give tests on Monday for that reason, but nevertheless, I think we need one additional day to do some things here in class before the test. So I did postpone that to Monday. So it's a Monday. And so I adjusted some of the due dates accordingly. I also put up here, so this is another extra credit assignment. So this is extra credit, right, because it's marked with asterisks. And so it's a quiz on these two assignments, 2.1 and 2.2, but it's extra credit. So if you make an 80 on that, you can get some currency, okay? 5 currency dollars for that quiz. It's only 10 problems selected from problems like 2.1 and 2.2, okay? Because I didn't think we would have time to actually take the quiz prior to the test, but I did put it up there for extra credit. And so that's due on the day of the test, along with, don't forget, the lengthy algebra review, okay? So a lot of y'all are close to the 82 on that, but not quite at the 82, so don't miss by a couple of points, right? If you're in the 70s or something already on this algebra review, make sure you boost your score up to 82 so you can get those 10 currency dollars, right, for finishing that review. And then also it will help you not make algebra mistakes on the test, all right? So that's kind of the sequence of events. We talk about that every day, but there it is up until the test. Also today, after class at 1, what Mr. Johnson mentioned last time, there's this Lunch and Learn series. This is the first of this series. So it's in A627 at 1 o'clock. So you can perhaps go after class to the SI session, and then come have some, it says free pizza there, okay? So I'm going to be there, but I won't hog all the pizza, all right? I'll leave some for you all, and you can meet the interim president. We're having a change in leadership here at UHD, so he's only been on the job, he's just the interim president, but he's only been on the job for a week or so, Dr. Olivas. So I haven't met him either, so I'm going to go and see what he has to say, okay, in A627, all right? Okay, I want to, there's one problem on this 2.1 that's, well, there may be multiple problems, but there's one for sure on this 2.1 that's annoying, and this happens sometimes on these homework problems, especially when I don't do the problem before assigning it. It's this one. Number 16. Yeah, that one is, that's just not a very good problem, okay? So if you're having difficulty with this problem, then it's just because the graph is really difficult to read, okay? They don't have a grid there superimposed on the graph, and so it's really difficult to estimate to the, the level of accuracy that they want the answers here, what these points are here that they have plotted on the graph. And so that makes it really hard to calculate these average rates of change. Okay, this one is a little bit easier because you can just sort of eyeball the graph, right? Okay, but actually trying to calculate these average rates of change, that one's pretty challenging. So if you're, you think you're doing it right, but you just can't get the answer to come out right, then that's probably what the issue is. Just the graph is difficult to read. So I'll probably have to adjust the scores to account for this problem, okay, which is worth 5 points. Let's see, can we answer the B part though? Because I'm not able to read that graph any better than you are, okay? Yeah. Oh, okay. So, oh, I see. So you were going to the closest 50 or something? Oh, okay. All right. So there's a piece of advice. John, you got it right because you got hundreds on all these. So were you able to?
Yeah. So I think it was just that one I was able to read and estimate well enough.
Oh, okay.
But when I get them slightly wrong for graphs that are hard to read, I just try things near them and keep trying until I get them right.
Okay.
I also have the benefit of knowing that what I'm doing is right, and so it's just wrong because I'm reading the graph.
Right. Okay. So yeah, that's the issue. You don't want to be, making a mistake that's really a fundamental mistake, and then think, well, I'm just reading the graph incorrectly, right? Okay. So on a test, so you may notice. Oh, I forgot to mention the practice test. So you may notice on the practice test that I think the graphs are drawn with a lot more care and with a grid superimposed, so that you can actually. If you're asked to do something like this, you can actually read the graph a lot more accurately, okay? We might be able to answer this one, though. It said, in which decade, maybe not, okay, was the greatest average rate of decline, okay? Well, we know it's not in the initial decades, right, okay? Because in the initial decades, the average rate of change is positive, right, okay? So in this case, the number of farms was increasing. That's what this graph purports to show, right? Okay, the number of farms in the United States. So there's not a decline there from 1860 to whatever that is, about 1930, right? Okay, it's only after the beginning of the Depression when the number of farms began to decline, okay? And so for what decade would the average rate of decline be the greatest? Well, that's just where the graph is steepest, okay? And that looks like right along here, correct? Okay? That's certainly where the graph is steepest, and that is from what, 1960 to 1970? Oh, okay. All right. So that's 40, 50, 60, 70, 80. Oh, all right. Yeah, you're right. So from 50 to 60? Okay. Yeah. All right. So right there for that segment, that decade, that's clearly right where the rate of the decline is greatest, okay? Because that's where the graph is going to be steepest. All right. So that one you can just eyeball. But trying to give accurate estimates there is a different issue, given the way that graph is drawn. Okay. Now I want to look at a couple of other problems here on not on that homework, but on the homework that's coming up. Okay. So remember that 2.1 is due tonight. Let's look at 2.2. So this one is due Monday. And is that opening for me? Yeah. Okay. And there are a couple of problems on here that I didn't. We hadn't really done a problem like this in class. It's kind of a review problem in a way, but I did want to mention it. Okay. So one of them is number 2. All right. So it says write a function for a linear model. That's kind of fancy, but what it means is write a linear function. All right, that will output the cost in dollars. That's important, to produce X toys. Okay, given the following information: the following rate of change. Okay, and then the following initial output value. All right. Okay, so what they're telling you in that first sentence here is, well, of course, write a linear function. So that's important to note. Okay, because when you are writing a linear function, you know what the formula is going to you know what the formula is going to look like, okay, when you get finished. Because linear function formulas, when they're simplified, look like this, okay? They always have that simple format, all right? So I'm using y is the output variable, x is the input variable. The m and the b will vary from linear function to linear function. But remember, they have important meanings, okay? This is the slope, of course. The m is the slope, right? Okay. Also known, however, as the rate of change, right? Okay. Because remember, for linear functions, the average rate of change is steady. So you don't have to say average rate of change for linear functions. You can just say rate of change because it's always going to be the same between any two inputs. All right? So they are actually telling you in that problem what the rate of change is or what the slope is, right? And the b, of course, geometrically, what does the b mean? Yeah, that's the y-intercept. But sometimes in practice, the y-intercept is called the initial value, okay? Because that will often give you information about where your linear function starts, okay? In some sense, all right? Well, let's look back at our problem here then, okay? So it says this cost is increasing by 40 cents per toy produced, right? Okay? So they're telling us the slope, all right? Okay? That slope is going to be 40 cents, all right? Remember, that's going to be converted to dollars, though, because we want our output to be measured in dollars. And now they're telling us here the fixed cost is $90. What that, in business parlance, what that tells us is that if we don't produce any toys at all, okay, we're still going to have a fixed cost of $90, okay? So we have certain startup costs that are independent of how many toys we actually produce, and apparently in this situation, that's $90. That is really the same as the y-intercept there. That's the initial value, okay? That's the cost that you're going to incur even if you don't produce any toys at all, okay? So what they're really telling you in, this is sort of business terminology, is the slope, okay, and the y-intercept. So you can just simply insert those into your linear function formula, all right? Okay, let's see there. So our slope is 40 cents, right? But we've got to convert that to dollars, okay? So let's type that in as dollars. Well, of course, 40 cents is $0.40, right? Okay? And then plus, we're going to add on there the y-intercept, right, which is that fixed cost of 90, okay? So that's really turns out to be a pretty trivial problem, all right, okay? Because they just simply are telling you the slope there and the y-intercept. So problem number 3 is very similar, okay? They're giving you the slope, right, okay, and the initial value, which is the same as the y-intercept, okay? All right. So if you were looking at that and wondering, I don't remember seeing an example like that. Well, we didn't actually do an example like that, but there's how we do that problem. All right, now, the next one is a little bit tougher, okay? So I want to look at problem, also on this homework, problem number 16, okay? So let me scroll down there. All right, so they're giving us here a function formula fairly complicated formula, x to the fourth minus 9x cubed minus 19x squared. And then they're asking us actually some fairly straightforward questions about this function. They want to know, is there a local maximum, right? And is there a local minimum? Apparently there's one local maximum and one local minimum. So remember, this is alternate terminology for the turning points, okay? So are there any peaks and valleys on the graph of this function, okay? Remember, I cautioned you that actually local maximum and local minimum refers to the y-coordinate of the turning point, okay? But they're actually using just local maximum and local minimum as the same as the turning point, because they apparently want both coordinates here, all right, okay, when you type in your answer. All right, so we're looking for where there's a peak or a valley on the graph. In other words, where the function switches from increasing to decreasing or vice versa. And then that's the second part of the question, right? Once you've located those turning points, then you can easily answer where it's increasing and where it's decreasing, okay? So we've done lots of problems like that, okay? But what's tricky about this problem is they're not showing you the graph, right? In order to answer this question, we really need to see the graph, okay? So we don't have the tools yet to be able to answer this question without looking at the graph, all right? So that's why the very first sentence there says, you're going to need a graphing calculator in order to do this question, all right? So what I intended for you to do is to make a graph of this particular function, look at the graph, and see if you can then answer these. See if then you can answer these questions, okay? You know, you're going to have to be careful now when you're looking at the graph because they want answers here to 2 decimal places, okay? So depending on how complicated those turning points are, right, that might be tough to look at the graph and actually see what the turning points are, okay? All right, so how are we going to make the graph? Well, you can do it with a graphing calculator, okay? So if you've got a graphing calculator and you're able to use it, that's fine, okay? But otherwise, let's use Desmos, okay? So if you're working on your homework, you can always use Desmos, all right? So again, I wrote just the address there for you on the whiteboard. Let me see if I can add a... this thing is in my way. Let me see if we can add another tab here to Google. And yeah, it's there, but I already have that one typed in, so I didn't want to disturb that one. Okay. So let's open another instance here of Desmos, and let's type in that. Let's type in that formula, okay? All right, so, I'm going to have to remember what the formula was, though, okay? So let's look back there. All right, so y'all help me remember. X to the fourth minus 9x cubed minus 19x squared. Maybe I'll remember that, okay? But probably not. All right, so go back. All right. So I don't think you even need to type in the y equal, but you can experiment with that, okay, and see if you need that or not. All right, so what was it? Again, x to the fourth, okay, right, okay. So let's put that in. And what, minus 9x cubed? And be sure you get the whole expression in right, because it's going to start graphing whatever expression you've got, right, as you're typing it in. So be sure you get the whole thing and don't stop and start looking at the graph. And then what was the last term there? Minus 19x squared? So minus 19x squared, okay? And we get a, well, not a bad graph there, okay? But it's not a great graph because part of the graph is cut off, right? So I'm going to have to do a little bit of adjustment here on my graphing window. Let's try zoom. So let's shift it up a little bit, right? So there are the 2 turning points, right? Okay, there are 2 turning points. Ooh, is there another turning point? Ooh, there's got to be another one, right? Okay, because here it has another x-intercept, right? So let's zoom out a little bit there. Wow, okay. Way down here, okay, is that another turning point? Well, we'll look for that one in a minute, all right? So we do have 3 turning points here. Let me zoom back in, and Let's zoom back in and look at these two first, okay? All right, so all we've got to do here is locate these turning points, right? Okay, and Desmos is very friendly, so it's going to give you a good estimate for those turning points, right? So write that down for me. There's one of them, minus 1.19, okay? So that might be minus 1.20 if we round it off to 2 decimal places. And then the y-axis is what? Minus 9.74, okay? Minus 9.74. And that was so what sort of turning point is that? That's a valley turning point. So you're going to type that into, is that the local minimum or the local maximum? Yeah, local minimum, right. Let's find this. Here's the local maximum. That one was easy. That's at 0, 0. So we don't have to really worry about the decimal places there. That one's exactly at the origin. And then this other one now, I'm going to have to go find. Okay, so let's zoom out again. Man, they didn't make that easy at all, did they? Okay. So way down here is that other local minimum. You know, and that looks almost like the graph comes to a sharp corner point there, but it's not quite. It is smooth, all right? If you zoom in enough, you really do have a smooth turning point there, okay? And let's see if it'll tell us what that is, okay? So apparently 7.95 and then minus 728.43, okay? Minus 728.43, all right? So you do have to do a little work there, moving the graphing window around in Desmos, right? Okay, to find those minimum and maximum values. Wonder if we have a chance of getting that one typed in right. Okay. So let's go back there. What was our local maximum? That was 0, 0, wasn't it? Yeah, okay. So that one I know we're going to get right, okay, because that one was pretty obvious. And then we have those two valley turning points, okay. So the first one was the one on the left there was what? Minus 1.20, we thought, rounding to 2 decimal places there. And what was the y value? Minus what? 9.74, okay. And then the larger one, all right, was, forgot, what was that one? 7.95, okay. And then that really small y value, which was what? Minus... No. 0.43? Oh, okay. All right. So, that's a pretty complicated curve to find turning points on, okay? But not so bad if you're just patient there and use the Desmos software, okay? So you can find them to fairly good accuracy. I hope we got them close enough there for the machine. So let's see, where was this thing increasing? Let's look back at Desmos for a second there, all right? And see if we can recall that where that was increasing. So remember, it's increasing between the turning points, right? Let's see if I can get that to scroll up. Well, we can probably figure that out, right? First it was it was a local minimum, correct? Okay, let me draw this one on the screen. All right. So we had a local minimum, right? Okay, first. So it was going down, and then it came back up, right? And then it was going back down again, right? Okay. So first we notice what? It's decreasing, right? Okay, and then increasing, right, up to this turning point, and then decreasing again, correct? Okay, and then it's going to be increasing again, right? Okay, so you've actually got a couple of places where it's decreasing and a couple of places where it's increasing. So it looks like it's decreasing from, Zaman, you want to say it there, from negative infinity to that first turning point, right? Okay. So let's see if we can get that typed in. So minus, was that in symbols? The minus infinity? So minus infinity to, where was that first turning point at? Negative 1.2. Remember, you're going to type this in interval notation, right? Okay. And then decreasing again from 0 to this turning point. Okay. So decreasing again. So, oh, you're right. So minus infinity to minus 1.2. All right, and then is it sets? And then again from, what was that second local minimum? I'm sorry, 0 to the second local minimum, which was, what'd y'all tell me? 7.95. There it is on the screen, so I could read that. All right. So decreasing there, and then increasing just in the opposite part of the, domain. So that's going to be from minus 1.2 over to 0. And then again from the 7.95 out to infinity. Okay. All right. So getting that one graphed and getting it typed in is a little bit of a hassle. But once you see the graph, right, okay, did I do that right? So let's see, increasing from minus 1.2 to 0, and then from here, which was 7.9 to infinity, right, that looks right, and then decreasing from minus infinity to minus 1.2, and then from 0 over to here, and we think that was 7.95, okay? Yeah. It's, oh, we already tested it there? So on this first local minimum, that one it's complaining about? Okay, so let's look at that one again. The other ones are coming out correct? Well, that's a miracle that the other ones came out correct. Aren't y'all happy with that? Okay, all right. Let's zoom way out here and see if we can get back over there and find that one. it's hard to see because of the. Let's reset our graphing window here. Negative 1.196, and it wanted it to 2 decimal places. So is it happier with 1.19? Let's try that. Still not? Okay. We typed the expression in right, didn't we? Let's try regraphing it there from -2 to 0. Okay. So there I can finally see it again. Let's zoom in. I don't know. Okay. All right. So that does look like minus 1.2, and what we said minus 9.74.
Yeah.
So it does look like, indeed, like it's minus 1.2. So I'm not sure why it's not.
That says -1.196.
Yeah, but when you round that off, it's going to be minus 1.20 again, right?
Yeah.
Okay. If you round that off. Or minus 1.19, so it's got to be one of those two. And then the second one is minus 9.7. That looks like 7.4, but maybe it wants 7.3 there. Okay. Let me check it. Okay, well, we're right. All right, so but I'll have to look at the answers and see what it wanted. I'll email y'all and tell you what it thought was correct. Okay, but that's the way you want to do the problem. All right, so on a test, that's what you're looking for. Okay, right? Okay, so I think you're doing it right again. It's just this awkward having to get the right number of decimal places there. Okay. I can see the answers, but I'll have to stop and look for that, all right, to see exactly what it thinks that is, okay? All right. So, but the moral of the story is there, right? To answer that sort of question, you're going to have to use the graphing software, okay? Until we learn how to do this without making graphs, okay? So there is a way of doing this without making the graph, but right now we're stuck with just making the graph, okay? All right. So there are a couple of problems like this in the 2.2 homework. All right, let's go back now to our example here. Get that off the screen. That we were looking at last time of the screwdriver falling, right? And so last time we managed to answer this question right at the end of class. How fast was the screwdriver dropping? So it was dropped from that building at a height of 400 feet. And we managed to answer the question, how fast was it dropping after 2 seconds? So remember the trick that we pulled there, and this is a really crucial trick now in the class, is we drew the graph, okay? We drew the graph, and then we zoomed in on that piece of the graph around x equal 2 seconds until that graph looked like a straight line. And our reasoning is, since straight lines have steady rate of change, okay, then the rate at which that screwdriver was falling after exactly 2 seconds, okay, would be whatever the average rate of change or the slope of that line is that we see when we zoom in on the graph right there around 2 seconds, okay. because no matter where you calculate or how you calculate the average rate of change for that piece of the graph that looks like a straight line, you're always going to get the same quantity, all right? So that makes sense to answer this question, how fast was the screwdriver dropping after 2 seconds, just by using that steady slope, okay, that steady rate of change. So let's do that again, all right, because that's actually the trick that we're going to be using to answer this question repeatedly, all right? So not just for this screwdriver, but in general for functions, all right? So let's try it again, but at a different time. So let's answer there. How fast was the screwdriver falling after 5 seconds, okay? So how fast was that screwdriver falling after 5 seconds? Which happens to be, here's the graph, not of the path of the screwdriver, right? But here's the graph of that function that we were using to determine the height of the screwdriver. And it so happens that we had already noticed, the screwdriver hits the ground after 5 seconds, right? Okay? And so essentially what we're answering here is how fast was that screwdriver dropping right when it hits the ground? Okay, so how fast was it going? We know now how fast it was going right here after 2 seconds. Well, at least we have an estimate for that. Our estimate right here was about, it was dropping at about 60 feet per second, okay? How fast was it dropping right when it hits the ground, okay? All right, so remember our scheme now is the same. We're going to take this piece of the graph, this little piece of the graph, and we're going to zoom in on it. We're going to blow it up until that piece of the graph looks like a straight line, okay? And then, again, our reasoning is, okay, if we zoom in close enough that the graph looks like a straight line, that means the rate at which the screwdriver was falling in that little interval, okay, the interval that looks like a straight line, that little interval of time where the graph looks like a straight line, that means that essentially, not exactly, but essentially over that brief interval of time, the screwdriver was falling at a steady rate, okay, because it doesn't have sufficient time to speed up, all right, in that little tiny interval, okay. And so the slope of that straight line that we see, okay, the average rate of change of that straight line that we see when we zoom in really close here to 5 seconds, that will be our answer for how fast was the screwdriver dropping at exactly 5 seconds, okay? Well, see, to answer this question again now, we've got to make the graph, though, okay? So somehow, because we have to be able to zoom in here on just this little piece of the graph, very close here to 5 seconds, all right? Okay, so I already made that. Let me see if I can find it. Ah, there it is, okay? So there's the graph that you see in that in the notes, all right? And again, we're going to zoom in on this piece of the graph right here at around 5 seconds. Notice that already looks kind of like a straight line as it is, right? Okay, but there is a little bit of curvature, so we want to zoom in close enough that we're satisfied that we can't really see any curvature in that graph, okay? That it appears very much to us like a straight line, okay? And actually, all curves are going to have this property if they are smooth and unbroken. That's one important caveat there, one important warning. If you have a graph that a curve, when you graph it, you get a smooth, unbroken curve. If you zoom in close enough on any piece of that graph, okay, where it's smooth and unbroken, eventually it's going to look like a straight line, okay? And so you can treat it like a straight line. The reason that's convenient is because straight lines are easy to work with, okay? That's probably the simplest type of function that we can deal with, okay? All right, so by the way, now notice that when I graph this on Desmos, of course, the curve continues past x equal 5, but that doesn't really happen in practice, right? Because the screwdriver is going to hit the ground here, right here after 5 seconds, all right? So really, this piece of the curve really doesn't actually exist, all right? Okay, so let's zoom in on that, okay, until we don't see any curvature in that graph at all, okay? So we're already pretty close to that, but let's go a little bit further in, okay? And I haven't tested the limits of Desmos here, but you can zoom in probably as much as you like, okay? Does that look like a straight line already to y'all? So if you just showed that to someone and asked them, is that a straight line, what would they say? Probably say yes, right? I can't see any curvature there, all right? So that looks very much like a straight line. Now, we know that, in fact, it's not a straight line, right? There really is a little bit of curvature there, but it's so small that, we can't tell what it is, right? So what we'll try to do is estimate the slope of this line. We're going to try to estimate the slope of this line, and that's what we'll use as the rate at which this screwdriver is falling. So we'll find the average rate of change of this line, which is the same as the slope of this line. Again, remember that's steady if this really is a line, right? Okay, and so that steady rate of change is a reasonable way to answer how fast is the screwdriver dropping after 5 seconds. Okay, well, now look, to find the slope of the line, though, what are you going to have? 2 points on the line. Sure, right, okay. So we need to identify here a couple of points on this line, okay. Let's see if we can get Desmos here to give us a couple of points. Oh, there's one, okay, on the line. Y'all see the coordinates there? So can y'all write that down for me? All right, so there's 1 point, 4.99 and 1.598, okay, 4.99 and 1.598. Now let me slide this down, and here's another point on the line, and I'm pretty confident what the coordinates of that point are, right? Because it looks like just what? 5 and 0, right? Yeah, sure. The screwdriver hits the ground after 5 seconds, right? So its height after 5 seconds is exactly 0. That is another point on the line. So you can use that point. If you're not comfortable using that point, though, you can come down a little bit further if you want to and get another point. So here's a third point, 5.01 and minus 1.602. Okay? Any 2 points on the line will do, though. All right, any 2 points on the line will do. That's what's so nice about straight lines, right? Okay, if you calculate the rate of change or the slope between any 2 points on a line, you always get the same value. Okay, all right, there it is. So let's just go back there now and plug that in. If I can get to the right notes, here we are. Okay. So how fast was that screwdriver dropping? Okay, so what was that rate of change after 5 seconds? Well, and I could put average rate of change because I'm going to use the average rate of change formula, but again, since we want just it's not really an average here that we're calculating because we're trying to find the rate of change exactly after 5 seconds, all right, so I can really just drop off the word average there. All right, and let's use now our slope formula, correct? Okay, so let's see, I did what, 4.99 and 5, right? Those were the two x values, okay? Or you could do 5 minus 4.99. Either way is fine. Make sure you do the subtraction in the numerator, though, in the same order. So what was the height of the screwdriver at 4.99 seconds? What was the y-coordinate that went with 4.99? 1 point what? 1.598. Okay, so 1.598. And then, of course, the height after 5 seconds, that's easy there. That was 0, right? Okay, so the denominator, that's so easy. That's minus 0.01. Even I can calculate that. Okay, and the numerator, pretty easy here also because we're just subtracting 0, right? So it's going to be what, 1.598, right? Okay, and so you're just going to take the 1.598 there and divide that by the minus 0.01. So you're going to get a negative amount. I messed that up in the example last time, but I fixed it in the notes. Okay, so you're going to get a negative amount. You're dividing a positive by a negative here, and you're dividing by 1/100th, which is the same as multiplying by 100. Okay, so it looks like all I have to do is shift the decimal place over a couple of spots there, and there we get it. Okay, so there's our estimate for how fast that screwdriver was dropping after 5 seconds, okay, or exactly when it hit the ground, okay, minus 159.58. Okay, so that would be, it was falling, right? Okay, at 159.8, and what's our units of measure there? Feet per second, right? Okay. So it's going pretty fast, all right? When it hits the ground, each second there, it would drop another, well, approximately 160 feet, okay? All right? So that's pretty fast, all right? Okay? So if that's, as I mentioned before, if that screwdriver hits you on the head, right? Okay, that's going to hurt, right? Okay, because it's going really quickly there, all right? Now, let me introduce here a little bit of notation, okay, that we're going to use, and I'll repeat it, the definition of the notation in the notes. But this rate of change now that we're calculating how fast the screwdriver was dropping after exactly 5 seconds, okay, we're going to use function notation to indicate this. So remember, the name that I gave this function was f. So to indicate this rate of change at exactly the input 5, I'm going to use this notation. I'll use the name of the function, but I'm going to put a apostrophe here above the name of the function. You don't read that as apostrophe, though, okay? You're going to read that as prime, all right? And then you just put the input right back in the parentheses like you always do in function notation, okay? All right, so look, if I just wrote f of 5 without the apostrophe, okay, if I just wrote f of 5 without the apostrophe, what would that be? That would be the height of the screwdriver after 5 seconds, right? Okay, so if I just write f of 5, that just means how high the screwdriver was after 5 seconds. Of course, that was what? 0. But when I write f prime of 5, that's how you read that. Okay, so you read that as f prime of 5. That means what was the rate of change of the function? The rate of change of the function after 5 seconds. Okay, all right. So this is just the function output. This means the rate of change of the function outputs. All right? So function and rate of change. And that's the notation that I'm going to use to indicate now rate of change. Okay? So a way to interpret that rate of change is that sort of gives you, that sort of tells you what the slope of the function is, what the slope of the curve is at this particular input, okay? The slope of the curve at this particular input. But remember, this is a curve, so the slope is not steady, okay? This is a curve, so the slope is not steady. So if you calculate the slope at a different input, you're going to get a different value, all right? Because this curve is not a straight line. So back when we were calculating how fast the screwdriver was dropping after 2 seconds, remember we estimated that to be 60 feet per second. How would we indicate that using function notation? Okay, so that minus 60, how would I write that down using function notation? Same idea that I did here. Okay, so what do you put? Yeah, that's right. You put the name of the function, right? And then you put the prime there, okay? And then what goes inside the parentheses? 2, right, okay? Because that minus 60 was the rate of change after 2 seconds. That's not the same, be careful now, that's not the same as f of 2. F of 2 is just the height of the screwdriver after 2 seconds. This is the rate of change of the screwdriver after 2 seconds. And you're going to get completely different values for these two quantities, okay? All right, so plain old f of 2 was just the output that matches the input 2. That was the height of the screwdriver after 2 seconds. F prime of 2 is what's the rate of change of the height after 2 seconds. Okay? Well, the height was dropping by 60 feet per second, according to our estimate from our previous looking at the graph, right? After 2 seconds. Okay? So be careful about the difference between those two pieces of notation and what they mean. Okay? That's just the output. That's the rate of change of the output, okay? And it sort of corresponds to slope, all right? So f prime of 2, that sort of tells us what is the slope of this curve, what's the slope of this curve after or at the input 2, okay? Right? But remember, this is a curve, so it doesn't have a steady slope. That's why when we calculated f prime of 2, we got a value, but when we calculated f prime of 5, we got a different value. See, the slope is not the same all the time. All right. For straight lines, the slope is always the same. But for curves that aren't straight lines, the slope can change from input to input. All right. Here's that. Here now is that definition. So let me show you the definition. Okay. And it's exactly what I just said. Okay. So suppose you have a function, some function, and you have an input value a. Okay. Then the rate of change, also sometimes called the instantaneous rate of change, but it's kind of hard to write out the word instantaneous all the time because that's a long word. So we often just abbreviate that to rate of change. All right. So the rate of change of the function at the input a, okay, what that indicates is the slope of the graph, quote unquote. I have to put that in quotes because it's not really a slope. Slope is something for straight lines, right? Okay. But it's quote unquote the slope of the graph at the input a. How is it denoted? It's denoted by this notation. So you use the name of your function with that prime symbol, okay, at whatever input. All right, let's try that now, okay, with another example. Okay, so here we have a nice function, f of x equal x cubed minus 5x, okay? I don't know how this function is being used in practice. Yeah, I don't really care, okay, in this problem. So I don't know what the x is measuring. I don't know what the output's measuring here. I've just given this formula, all right? So the first question there is very straightforward. They just want us to calculate the average rate of change. Well, you know how to find the average rate of change, right? Okay, so you know how to find the average rate of change. You just use your average rate of change formula. So I'm not going to go through all the calculations here because we've done this now plenty of times, right? Okay. But what do we plug into our average rate of change formula? Well, there's the first value, there's the last value, right? Okay, so it's right. Minus 1 minus a minus 3, right? Okay. And then what? F of minus 1 in the top minus F of minus 3. Okay, so that's just the average rate of change formula. All right, and so this is easy to compute in the denominator, and to find the numerator, you just plug in. Oops, I forgot to put the minus on the 3. Okay, but to find those numbers in the numerator, you just plug minus 1 into your formula, and you just plug minus 3 into the formula. Y'all can't see that minus sign. Let me fix that. You just plug minus 3 into the formula and do the math. Okay, so very straightforward. All right, we've done that now in the homework several times. All right, now here's what's the more interesting problem. Okay, let's find f prime of minus 2. Okay, so not what was the average rate of change from from minus 3 to minus 1. Okay, but exactly what was the rate of change at exactly the input minus 2, okay? Or another way of thinking of that is, what is the slope of the graph at the input minus 2, okay? All right, how do we figure that out? We don't have a formula for this yet, okay? We don't have a formula for this, so how in the world are we going to get an estimate for f prime of minus 2? Well, what do we do with the screwdriver graph? Yeah, but before you found the 2 points, what do you have to do first? Graph it, right. So we're going to have to take that formula and graph it, okay? So we're going to have to take that formula and graph it, x cubed minus 5x. We're going to have to make the graph. And then, what do we do with the graph? So let's make the graph there. I've already changed this graphing window, so this is... Let's close this one. Let's start a new instance here of... let's start a new instance here of Desmo, so make this a little bit easier to start from scratch, okay? So we're just going to make the graph, and once we have the graph made right, then what do? So that's part of making the graph, right? So we have, was it x cubed, right? Minus 5x, okay? Whoops. So x cubed minus 5x. Oh, there's the graph, all right? Oh, so this one we can actually see pretty nicely, okay? So there's the graph, right? So we can see, I think, all of the turning points there. I hope that's all of the turning points, all right? And once we've got the graph, right, to find that slope at the input minus 2, what will we do? Zoom in, that's right, okay? So we're going to zoom in on the graph, and where on the graph? Right around where? Right around minus 2, that's right, okay? So we're going to zoom in on the graph right around this point until the graph looks like to us what? Just like a straight line, okay? All right, let's see if we can do that then. Okay. Ah, that's interesting. Okay, I thought minus 2 was where it was crossing the x-axis, right? Okay, but it's not crossing the x-axis at minus 2. All right. It actually crosses a little bit to the left of minus 2. Does that look like a straight line to you guys? Yeah, pretty close, okay? And you've got to get minus 2 in your picture, all right? So you've got to make sure you've got minus 2 in your picture, because if you don't have minus 2 in the picture, then you've got problems, okay? All right, so there's the input minus 2, right? Okay? And we've got to calculate the slope there of this almost vertical line, right? Okay? So, because that will be our estimate for that slope at the input minus 2, okay? Right? Okay? That will be our estimate for that instantaneous rate of change at minus 2. All right, now, so we've got to pick a couple of points off of this line. All right, you can always use this point you can use, all right, if I can get it to give me that point, okay? If we can't, oh, there it goes, okay. All right, so what is it at minus 2 there? 2? Yeah, okay. So minus 2 and 2 is a point on the graph, and then let's find some other point on the graph here, and you can pick any other point that you like, all right? So you can either eyeball this or you can point at it, right, okay, and get some other point there off the graph. So one point there is minus 2 and 2, okay, and then let's slide it up a little bit and get another point. So there's a nice one. What about minus 1.99 and what's the y-coordinate? 2.6094? 2.6094. Okay, did y'all write that down for me? Did I say that wrong? There's 1.99 and 2.0694. Yeah, I said it wrong. Okay. Did y'all write that down? Okay. All right. So let's go back here now. And so our estimate now for f prime of minus 2, right, is going to be, now you just calculate the slope between those two lines, okay? Just calculate the slope between those two lines, all right? So let's see. One of the inputs there was 2, right? Okay, I'm sorry, minus 2. And the second one was what? Minus 1.99, right? Okay. So I'm going to take the difference in those two values, okay? And then what about for the top there? So the output at -2 was 2, right? And what was the output at 1.99? That was one I kept messing up. But what was it? 2.0694. Okay. So give yourself plenty of decimal points there. So this is -2 plus 1.99. Okay. So the denominator is going to come out to be negative, okay? And then the top there also is going to come out to be negative. That's going to be 0.0694, right? But now once you filled in those values, it actually gets to be pretty easy. So you have -0.694, and you're dividing that by -0.01. So you have negative over negative. So it's going to come out to be positive, right? Okay, and you're just taking this when you divide by 0.01. That's the same as multiplying by 100. So I can just shift that decimal place a couple of places. So it looks like there my final result is what? 6.94. There we go. Yeah. So there's my answer to my question. Okay. So that tells us the rate of change of that function right at -2 was 6.94. How do we interpret that now? So what would be our interpretation of that number? What's that 6.94 telling us about our curve f, okay? The graph of the function f. Well, it's a little bit hard to interpret this one because you don't have a context, okay? But we can still write down an interpretation, okay? You've got to start, though, with at the input, okay? So don't leave that off, okay? Because remember, this rate of change is going to be different at different inputs. The slope is not steady for a curve, okay? So what we have calculated is the slope right here at the input -2, okay? All right, so at x equal -2, let's see what's happening. The output values, right? And I don't know what those outputs are measuring, so we just have to say outputs. Are they increasing or are they decreasing? They're increasing, right, okay? By how much? 6.94, and then the last part is really important because you've got to throw in that per, okay? Well, we don't know what the inputs are measuring here, so we don't know if this is time or weight, so we just have to be sort of very vague in our per here. I would just say something like per unit change in x, or you could say each time x increases by 1. So right at the input -2, okay, the outputs are going up by this amount every time x goes up by 1, okay? But that doesn't last very long because if you look back at the graph, let's zoom out again, okay? There's the -2, okay? So there's the -2 right there. You can barely see it, right? But right there at -2, the graph is going up by 6.94 every time x increases by 1. But that doesn't last very long because what starts happening to the curve as you get a little bit here to the right of x equals -2, what's happening to the curve? It begins to what? Yeah, it begins to peak out, right? Okay, and so it starts to flatten out, and then you hit this turning point, and after that turning point, what's happening to the outputs? They're actually doing what? Yeah, they're actually decreasing. So on this part of the curve, notice the slope is going to be negative, right? Okay, On this part of the curve, the slope is going to be negative. That lasts for a little while until this turning point, and then the slope of the curve gets positive again. See, that's my point. For curves, the slope, the rate of change is not steady, right? Okay, because the curve is wiggling. Sometimes it's increasing, sometimes it's decreasing. So that 6.94 that we calculated, that just tells us what's happening right around x equals minus 2. Okay? All right. We have got just enough time now, okay, did y'all keep this sheet? Okay? So, all right, so John will give you a copy. I didn't bring enough for everyone, so I hope most people brought it, okay? All right? Because I want to give y'all a little bit of practice here with this, okay? Let me see if I can get the dot cam to work here. That's not bad. Okay. So everyone got this one? All right, so this first question now is kind of a tricky question because it's asking you about this function, so this curve, right? But at what input? Yeah, at the input 3, which is right there in the middle of the graph. But notice it's asking you why is not f of 3, but why is f prime of 3 undefined? By the way, what is f of 3? Not f prime of 3, but what is f of 3? Okay. Yeah, that's 0, right? Okay. You just read that off of the graph, correct? You know the output is not here because this is an open circle. In fact, the output is down here, which is 0. All right. So f of 3 is defined, but the question is, why is f prime of 3? Why can we not calculate that? Why is that undefined? Well, think about it. If we were going to calculate this, what would we have to do? Yeah, you got to find the slope, right? But to find the slope, you have to do what? You have to be able to zoom in, right? Yeah, you have to be able to zoom in on that graph until it looks like a what? Is that ever going to happen if you zoom in around 3? No, okay? Why not? Because the curve right there is what? It's broken, you see, okay? The curve right there is broken. So that's why f prime of 3 is not defined, okay? The only time you can use this trick of zooming in until a graph looks like a straight line is if you have a smooth, unbroken curve. Smooth is really important too, okay? Must be smooth, okay? And it's got to be unbroken. So any place where the graph is broken or not smooth, by not smooth I mean if it has any sharp edges on it, okay, not going to have a rate of change, okay? Not going to have a rate of change there. Not going to have a slope there, at least not one that you can calculate, all right? So the reason f prime of 3 is undefined is the graph is not a smooth, unbroken curve at x equals 3. That you have to have, all right? Okay, well, all right. That's not what we're asked here in this question, though, fortunately. What we're actually asked here is, what is the rate of change at 4? Okay, so we want to calculate the rate of change at 4. And how would we denote that with function notation? So before you actually calculate it, how do you write down the rate of change at 4? So what's our function notation for that value that we're getting ready to calculate? Yeah, see, that's so easy, right? Okay, f prime of 4, right? You just use the name of the function, which in this case is f, right? Okay, see, we were given that. The name of the function is f, and we're going to find the rate of change at 4. Now, I wonder if we can do that. Well, let's see. Close to 4, do we have a smooth, unbroken curve? Yeah, around the input 4, not over here, but at least close to the input 4, we do have a smooth, unbroken curve. So it looks like we can estimate that rate of change, okay, by blowing up this little part of the curve until it looks like a straight line. All right, well, that's what I've done in A, B, C, and D. I've blown up a piece of the curve, okay, and but the question is, okay, which one of these graphs can I use to determine what that, or to estimate what that rate of change actually is. All right. So it's either A, B, either 1, 2, 3, or 4. Let's see. Is it the first one there? That one looks pretty good, right? Does that look like a straight line? Yeah. Okay. And have we blown it up around the input 4? Yeah. There's the input 4. Okay. So you might not believe it, but if you blow up that piece of the curve at the input 4, that's what it's going to look like. Okay. What was wrong with this one? That's just the whole graph, right? Okay. Yeah. At the input 4, does that look like a straight line? No, we can definitely see the curve there, right? What was wrong with 3 and 4? Yeah, in the third one, you can still see the curve, right? Okay. So that's not going to give us a very good estimate. And what was wrong with 4? That was a trick question. Yeah, we blew up the wrong part of the curve, right? Okay. This is close to the input 5, okay? So if we were trying to find the rate of change at the input 5, this would be good, right? But not at the input 4, okay? Not at the input 4. We've got to blow it up around the input 4, okay? Oh, all right. So there's the last part. All right, so do that for me now. Estimate that rate of change. So you know you're going to use this curve, right? Okay. So estimate that instantaneous rate of change at the input 4. Okay. You got just enough time to do it. So pick 2 points on there, any 2 points you like, okay? And use them to calculate the slope of that quote-unquote straight line. It's not really a straight line, but it looks like a straight line to us, okay? So you can talk with your friend if you see if y'all got roughly the same number. Everyone might get a slightly different number, by the way. Okay, all right, because you may pick off different points. All right, and this is kind of the flaw in our scheme, is doing it, estimating the instantaneous rate of change this way means different people can get different results. And that's, in the long run, that's not going to be good because we've got to have everyone giving the same answer, right? Okay, so we can already see we have a flaw in our way here of estimating the instantaneous rate of change. But it's a good way to get started on it. Now, if you look at the practice tests, I hope you will, there's going to be problems like this, exactly like this problem, where you'll be shown a graph that's blown up, and it'll ask you to estimate the instantaneous rate of change at a particular input. All right, so let's pick a point there. This one is easy. Here's an easy point to pick. Right at 4, because the output is so easy to read there. That's 1, right? Okay. So 1 point on the graph is 4 and 1, and now we've got to get another one. And you want to pick one that's pretty obvious. How about this one? Is that okay? Yeah, that's right at a grid point there. So that is, or you could have gone down here. That also would have worked, right? But if we use this one, that's going to be 4.04 and what? 1.02? Okay. So that one's pretty obvious. And now we just calculate the slope, but that slope is going to be that rate of change, okay, that we're trying to calculate. Again, I dropped off the instantaneous because that gets so hard to write out. Okay, that word is such a long word. All right, so let's calculate that slope. So let's see, that's 4.04 minus 4. Take the difference in the x-coordinates of your 2 points, right? And then the difference in the y-coordinates, 1.02 minus 1. So you come up with 0.02 over 0.04. And that's pretty easy. Is that 1/2? Yeah. That must be it exactly. Okay, how could we have missed that? All right, so it looks like our rate of change is exactly 1/2. So right at the input 4, when x increases by 1, the outputs, the y value is going up by 1/2. That's what the rate of change is telling you. Okay, at x equals 4, the outputs, the y value is changing by 0.5, is increasing by 0.5 when the x goes up by 1 unit per unit change in x. But that doesn't last very long. That rate of change doesn't last very long because what's happening to the curve? It's bending down, right? So this part of the curve isn't increasing as rapidly as this part of the curve is, right? Okay? So that rate of change is 0.5 at the input 4, but not going to last very long, right? Okay? A little bit to the right of 4, the rate of change has already slowed down some, okay? All right, so, wow, we've learned so much this week. Man, my head is just spinning, okay? We've learned so much, and this is really the idea that we're going to continue to exploit, but we have to think a little bit more carefully because you're not going to always be able to make a graph and zoom in on it, right? Okay? So how do you do this without having to make the graphs, right? Okay? So we want to think about that, but we'll take that up next time, okay? All right.